open quantum systems as well as quantum optics, right? So cavity QED and so on. So this is kind of like, let's say, the pi to the 4 in some sense of this world, right? Of open quantum systems and cavity QED and things like this, right? So, all right. So in its let's say simplest form, right? The model describes a single bosonic mode, right? So like you can think like a photon in a cavity, coupled to a set of n two-level systems, right? So you have n two-level systems. And they are coupled to each other. And so I will not go through sort of like the derivation of this, right? So it's not, let's say, as trivial as it may seem, right? But this you can think of this. So like the atomic degrees of freedom are approximated in a two-level fashion, right? And the interaction is this sort of like dipole interaction approximation, right? So you have a dipole in an electromagnetic field, right? And then with only, let's say, one mode, right, selected via the cavity. So you may notice this 1 over square root of n prefactor, right? So can maybe one guess sort of like why it's there? No, there is, yeah, I mean, let's say in some sense there is like no spatial structure, right? So it's just sort of like there's no.
For the Bladian terms, has like a well-defined thermodynamic limit.
I mean, at this point, there is nothing sort of like, let's say, that there is no Lindbladian anything, right? So it's just Hamiltonian, but yes, it's exactly this, right?
Yeah, because this is to be to see, because in the Lindbladian form, we were gonna have a product of things, you're gonna have 1 over n, then you solve it. That's...
Yes. And one, I think, simple way to sort of like see that this is the right prefactor, right, is that if you now, let's say, because you see like the bosonic degree of freedom is like, so the Hamiltonian is quadratic in the bosonic degree of freedom, right? So if you think about like some path integral, it's like Gaussian, it's Gaussian with respect to A, right? So you can just integrate it out. And then what you would have in principle is something that this, and this term is linear, right? So if you remember, then this would lead to something like 1 over n. Then you would have something like this, I, j. And so now you see that, so this gives you n squared, like it scales as n squared, and this scales as 1 over n. So overall, the whole thing scales as n, so which is extensive in the system size, if you wish, right? But in n. So this is why you have this 1 over square root of n. I'm sort of like, let's say, emphasizing it because this n will play a significant role in the further discussion. That's very nice. Okay. Let's say we have so from this, let's say I simplify, right? So what you have here, right? If you put this on a path integral, all of that, right? So you say you have something like, say, minus f squared, phi squared. So again, I'm very like sketchy here, right? Plus, and then you have phi, right? So a is like phi is a, right? Times let's say j, right? And you may know that like the result of this Gaussian integration, right, it gives you something like okay, in this case it's going to be something like a squared, right? So you see that, let's say, if you sort of, or you can like, in other words, you can adiabatically eliminate the photon degree of freedom, right? Or I mean, let's say let's even make it diagrammatic, right? Or maybe not. But you can see that sort of like the photon couples to the spin, right? And this it essentially induces interactions, right? So you let's say, okay, you have a spin, right? And then you have a photon, right? And then sort of this photon, let's say that the spin flips, right? It emits a photon, and then this photon can be absorbed by another spin. So this thing mediates interaction, all-to-all interactions between the spins, right? And all-to-all interactions is exactly this, right? So this is basically the integrated version of the all-to-all interaction mediated by the spin, right? And there's, I mean, and the whole thing scales as n squared, and it would be bad because it would be like super extensive, right? We wanted to have it be extensive, and thereby we add this so-called cuts prefactor, this so-called cuts prescription to make the whole thing extensive in the system size.
So you're going to integrate bosonic degrees.
No, we are not going to do this, but it's just sort of like, I think it's the simplest way to see why it's 1 over square root of n. See? All right, we don't. All right. So this is our model, right? And I mean, okay, so just for the sake of, let's say, fitness, right? So these are our usual bosonic degrees of freedom, right? And then these guys are staying. Yeah, this is kind of important, right? So that I'm actually here I actually consider here spin 1 half operators, right? Not the polymatrices. Thereby the commutation relation is this. It's without 2, right? So this is proper like SE2 algebra. Right? And also this is going to be important, but I hope you're familiar with this. So normally, like if I have like gamma gamma, right? So it's like the Einstein convention is applied. All right. Now, what we should also notice, right, immediately, that the dependence of this Hamiltonian on the spin degree of freedom, right, comes only in like this combination, right? So it only actually depends on this atomic degrees of freedom via, like, let's say total spin, right? So, or as I like to call it, like flat spin, right? It's cool. So the actual dependence on the spin degrees of freedom comes in this form, which sort of already maybe suggests you, right, that the, let's say, that as for large n, right, the description is going to be, let's say, the larger the n, the larger the system, the more classical description will be, right? Because you can imagine, I guess, that if you have many, let's say, yeah, so when you have many, so let's say entities, right? And so then like the sum of them, right? So like, what is this, like large number theorem from probability, right? So when you have a sum of random variables, right? So the overall sum sort of like the sum, sort of behaves like in a Gaussian fashion, right? So like if you add like many random variables, then the overall result will be like Gaussian distributed, right? And Gaussian distributed is essentially, it's like one way of saying it's basically classic, right? Because there are like no higher order fluctuations. So this is something that will later show properly, but I think it's already like now we should sort of realize that even though the system is many-body, but it's not like, you know, it's an innocent version of a many-body system, right? So in reality, it's let's say quite one-body, right? So like the many-body effects are suppressed at large and at the large system size, right? And we will see this, let's say, in more detail later. All right, so schematically, right, again, in the following, we will focus on the non-equilibrium case, right? So there is also, let's say, studies on the, and it was the original, let's say, case, right? So the Dicke, so Dicke, he considered the equilibrium case, of this model, right? But we are going to consider the non-equilibrium case, which is subject to both this sort of like coherent driving, right? I mean, here we already went to the rotated wave like the rotated wave and did all this stuff, right? And also subject to dissipative losses, right? So schematically, again, the experimental setup is actually like far less innocent than what I'm going to sketch, right? But roughly speaking, this is what you can imagine. Oh, by the way, yeah, so I should probably mention very nice, a very nice reference, right? So for sort of like to introduce to the Dicke model, right? Which is by Kirtan, Roses, Keeling, and Dalla Torre. Maybe I butchered the names. By 8005. 9, 8, 2, 8. I think this is like a very nice general introduction to the Dicke model. Right? Very nice reference. Anyway, back to business. So yeah, so the setup is roughly following. You have something like this. So these are like this is the cavity, right? Yes, let's say some driving field. Or pump. Then you have your atomic cloud. Third, other. Okay. So atomic cloud. This is atomic clouds, right? So our, if you wish, two-level system, right? So then, yes, so then inside the cavity, there is this cavity, selected cavity mode. Okay, I mean, it's not very visible, right? But cavity mode. Right, and then this system, so like the cavity is imperfect, right? So basically, like, yeah, so you have some driving fields, right? So like you have some photons ingoing, right? So they rescatter and so on. The ones that are in resonance with the cavity are sort of like can stay in the cavity, but like because it's still like the cavity is imperfect, some of them may escape, right? You have potentially cavity losses. So this is roughly, let's say, the setup, right? And
So far, the driving field and the cavity losses you haven't described yet, right?
no, I mean, in
just
principle,
describing.
no, cavity losses I haven't described yet, but the driving field can be sort of like already. So in principle, okay, so in principle, what you have is, of course, so like if it's the driving field, right? So this thing will be sort of like a time dependent, right? So you have some electromagnetic field,
Okay, so.
but then you go to like the rotating frame
Okay.
and all this. So essentially this frequency would be shifted and so on and so forth. In principle, also you should distinguish between the photons in this, like in the cavity sort of, and the one on the outside and so on. But this is all taken care of, let's say, by this Hamiltonian, right? So this describes, let's say, interaction of this like let's say of the atomic degrees of freedom and the photon, like cavity photons here, right? And also, let's say if you wish, like the pump.
But the part that I don't get is that if you're pumping something inside, the dynamics should be non-unitary, right? Instead here is the unitary because it's just an Hamiltonian.
No, I mean, this is the, like, this coherent pumping, right? So where you simply, you couple, in, let's say, yeah,
Okay, so your system is RDC.
yes,
Okay.
this is, and the, let's say the non-unitary part comes from the potential. So because I think what we are considering, right? So like the degrees of freedom that we're interested in are like like the cavity photons, right? So the ones that are like selected by the cavity and the atomic degrees of freedom. And the non-unitary part comes from potential leakages and all this stuff, right? But the driving, right? I mean, it's let's say it's like just coherent, like coupling of the electromagnetic field with the. I mean, again, so I sketched this. There's let's say far more going to get from, let's say, even this cartoon and like the actual experimental setup alone to this. But like if you do like certain like approximations and like, you know, do things carefully, right? So that like this captures, plus the losses captures this setup.
So I will tend to this that in the total description, you will have also a term that put energy into the system, right?
But yes,
This is not here yet, right?
I mean, I think it is here already. It's sort of like it's probably like it's let's say it's less evident because sort of like okay, if I instead had here some time dependence, right? So let's say, like, would you then say
Okay.
But then like sort of we go to the rotate.
Okay, got it.
Is it clear? Or anyone else was not like.
Not yet in the rotating frame because you are.
Yeah, well, no, I mean, yeah, but like, no, I mean, it's in reality, sort of, I already like went to the rotating frame, rotating
You
frame.
have the free Hamilton?
Free, in which sense is free?
The free part of the Hamiltonian, I'm convinced that that part has been already dropped. You are.
No, I mean, I go to the, no, because the let's say the pumping, the frequency, the pumping frequency and the like I mean, so the attitude. So here you should understand this as, let's say, omega minus omega pump or something like this, right? Or like omega cavity minus omega pump is equal to omega.
Okay.
If they were like perfectly in sort of like in resonance.
Resonance would be.
Yeah, exactly.
But they are not. Okay.
Exactly. Okay.
Just sketch the relation of terms with what I just drawn.
Well, okay. So yeah, so this term, right? It's this, right? So you have, let's say, excited ground. So like you approximate your atom as a two-level system, right? So which can be either in the ground state or in the excited state. And this is described by this, right? So you have your detuning. This thing is the cavity mode with frequency omega naught, right? So I mean, as discussed, sort of like with all these caveats. So basically, these are like photons that have this, you know, frequency, right? So like one oscillator, and then finally this, right? It comes from the interaction between the atomic, like these two-level atoms and the electromagnetic field, right? So this is, yeah, I mean, okay, you need to do like some, but like look at the, let's say, dipole approximation, electromagnetic field, like two-level system. Like, you know, like these are like the keywords in English, right? But I mean, it's like, but it makes sense, right? So that like you can absorb the atom, absorb a photon, right? And go from the ground state to the excited state, or vice versa. In principle, you can go from the excited state to the ground state and emit a photon, right? And this is the thing. I mean, this is what it does, right?
Right, if you just change the
So the driving, okay, so yeah, I mean, it's, as I said, I mean, it's a bit more complicated, right? So you have the driving field principle like this, like it has some time dependence. In reality, it might have, I mean, it actually even has like special dependence. It's very complicated. Let's say there's some time dependence, right? Because it's an actual, let's say, electromagnetic standing wave, for instance, right? But then you go to the rotating frame, removing this type dependence. In turn, it would shift this frequency and so on and so forth. Okay. So as I said, I mean, like, I strongly suggest like go through this reference and maybe many more, because despite its, let's say, simplicity, right, apparent simplicity, that there is, let's say, a lot of things going to this, like to get to this point, right? So it's. But for us, what matters is that, okay, we have this model. It describes cavity, or let's say, and two-level system situated in a cavity with potential losses, right? And now we want to apply our by now beloved Lindblad formalism, right? So what we have is this. So we have the unitary part and plus potential losses, where, oh, no, that's just fine. Where, as usual, I mean, I think it's worth repeating every now and then, right? Where as usual, and depends a bit on the convention, right? So you can also, without like this tool, right? This is what I usually use. But, taste. Right, and what are potential like main sources of dissipation? This thing. So, all right. Here we would have rate, the corresponding Lindblad operator, and finally the corresponding physical process. All right. So first of all, A, the rate kappa. So what is the corresponding physical process?
Decay, emission.
Cavity loss. Yes. So like that the cavity is not perfect, right? So like some photons, like the one, you know, like with the with the cavity frequency could still lead the cavity loss. Okay, now principle we can also have like this. So what would this be? So that like it's, you know, can go from the excited state to the ground state, but like collective. Yeah, but because it's, you know, say overall, right? So it's collective. So, or like when like all the atoms do this coherent fashion. Then there is say a single atom version. Finally, I mean, I'm not sure if you're familiar with this, but this describes dephasing.
In the x-axis is bound.
I did that. Oh, no. I think in my case it was not like the dephasing, was it? It was something a bit, I think, even more.
Hold the jump operator when it is emission. It's a noisy kind of count.
Anyway, yeah. So, but I mean, like, okay, we did have dephasing, but I think my Well, I mean, it's the thing that sort of kills your off diagonal entries, right? And let's say, okay, how to put this like physically, right? So like, let's say you have like n spins, right? And if they are coherent, sort of like, so like each of them, of course, induces, let's say, local magnetic field and so on and so forth, right? So let's say if they're all coherent, right? So they, like, let's say, precess like together, in a unified fashion, so to say, right? So, but like once, if let's say once is sort of like starts like perturbing, right? And it also like perturbs, let's say, the local magnetic field, and then everything sort of starts like synchronizing, right? So this is sort of like one way of like more classical way of thinking about like what is dephasing, right? I'm not sure, like, okay, if there is like a very simple way of like seeing that the corresponding operator is sigma z for the dephasing of a qubit. Maybe someone knows. Is there like a very intuitive way to see that like the dephasing operator for the qubit is sigma z?
I mean, maybe a student. Maybe student were talking, I heard the sound, but.
Yeah.
Because the sigma z is 1 minus 1, so you keep every state where they are, you're just changing their phases, flipping their phases.
Yeah, well, I mean, but in my opinion, this is a bit more mathematical. Yes, you can show that, like, if you like do something like this, right, then like on the diagonal you won't have anything, but like on the off diagonals you would have like the phase vectors and so on. That sort of, I wouldn't say this is necessarily physical, but
So I think, but I'm not sure, because sigma c comes with your Hamiltonian, then energy is conserved, so it only produce.
I mean, it doesn't consider, it doesn't.
I mean, in a single qubit.
Ah,
So if you have like a qubit that is sigma c and you put this as a Libra, then this commutes. I mean, with commutes.
okay.
Your Hamiltonian, and only the energy will be the population, but okay. Because
Mhm. Okay, so there's, yeah.
No, sorry, that's where I was mentioning your exercise. So maybe I didn't follow the exercise on that day. So perhaps that's why my comment will not be a resonance. But you remember that I asked you to solve this small thing when the jump operator is an emission spin operator, so it's a polymetrics. Then the linear dynamics is equivalent to an Hamiltonian with a noisy classical field coupled to that operator. You remember that, right? And Alex solved that.
There was sigma y.
Oh, but that's the thing, right? So you had sigma y and which Hamiltonian you had?
Sigma z.
Exactly. So that's the source of confusion of calling this the physics. If the field is not competing with the Hamiltonian, as some of you said, there is no reason to call it the phasing, because you will get both both relaxation in the diagonal, and you will lose coherence that people call dephasing. So you will get both what people call relaxation and dephasing, and there is no reason. But when your Hamiltonian commutes with the jump operator, then in that case, traditionally people call it dephasing because, as many of you said, only the off-diagonal guys will die. So it's an abused term, dephasing, for the sigma c.
Copy.
There is nothing we can.
Sorry, the last two gammas are dependent on J, they are functions of J, right?
Ah, well, yeah, but yes, but I mean, you can also imagine that like it's let's say it flips a single one, but like the let's say the rate is the same for everyone.
So what is the difference between the second and the third?
One is second and the third.
Yeah.
So like one affects affects the, let's say, the collective speed.
No, they understand, but
And one is
the
individual.
gammas are the same for every, either
Ah.
you decide to
I see what you
select
mean.
the specific or.
I see what I mean, but like, wait. But I mean, I'm like, let's think, let's say physically, right? I think in one case, let's say like instantaneously, sort of like so because in one case, like you instantaneously, you can only, let's say, decay, like, everyone decays at the same time, right? And in the other case, even though like they're decaying at the same rate, but they may still like one, and that's like, you see.
Okay, probably the point is that you to, let's say.
Here it's, let's say, conditional.
First,
Conditional, so that like, if they decay all together. Here, if they can maybe at the same rate, but
okay,
they can.
probably, let's say, mathematically, in the first term, L, rho, and Dicke, in the first case, you have two independent summations, J and K, one entering in N and the
Yeah.
other entering in dagger. The other, you have just one sum side, okay?
All right. Okay, good. So this is the setup, right? And yeah, importantly, so in the remaining of this lecture, right? So we will consider only the cavities. We ignore all other sources of dissipation. All right, so then,
So can comment, remember in the first lecture, I said at a certain point at the end of the course, you would have seen a model that can be interpreted also as a quantum system itself without using linear equation. Well, if you set all the dissipation equal to 0, you can still see the Dicke model as the problem spins coupled to a photon, and you can see one the graph of the other. Well, the 2PI, Alex will show you how to solve this without resolving the linear equation. So it's a composite system where you can consider, let's say, a boson in the graph of spins if you want. And if you set all dissipation to 0, right, it's a unitary problem, but still is composed of two parts. And you will see how 2PI doesn't need linear to make calculations, doesn't need to go small g and stuff like this.
all right. So what I think I will click. So the point is now, okay, one can essentially show / guess physically, right? So the driving field, right? It controls the strength of the interaction between the atomic degrees of freedom and the photon, right? So now you can already sort of imagine, right? So as you increase the strength, right? So like you pump stronger and stronger if you wish, right? So initially maybe like let's say so yeah. Basically, right, so you inject photons, right? They rescatter. Some of them are let's say getting so some of them leak, right? Some of them are like rescattered again, and so on and so forth, right? So even if you start in the vacuum case, right? Because of this sort of like eventually you will have, let's say, a certain number of photons inside your cavity, right? And it turns out that as you increase this, like make the pumping field stronger and stronger, or likewise, sort of like will increase the strength of G more and more, the cavity mode becomes macroscopically occupied, right? So you have what is called photon condensate. Right? So yeah, so that say your expectation value of A is non-zero, and also actually quotient. But and this transition is called the super radiant transition. So the emergence of a macroscopically occupied photon field inside your cavity. Right? Now, as you may know, so phase transitions, right? At least the like the ones that are continuous, right? Can be related to some symmetry breaking, right? So some spontaneous symmetry breaking. So what is the symmetry in question in this case, right? So what is the symmetry that is getting spontaneously broken in the Dicke model that is responsible for the superradiant mutation?
The speed rotation of the ground state. Like when you add the sigma x, you break this.
No, I mean, let's say, no, this is our Hamiltonian, right? So we don't change it, right? So what symmetry does this Hamiltonian have, right? There is one discrete symmetry, which by the way, has been sort of like mentioned in the lecture, I believe, right? So what do we have? Okay, so for instance, this has U1 symmetry, right? So you can like change the phase of your photon field, right? And like, you know, there will be like A dagger will compensate A, right? However, it will not work here, right? Because like this is all right. So what else is this thing invariant under?
Extension.
Kind of, I mean, this would be U1.
The field was actually extension on this.
Yes, we will sort of like come to this, right? But let's first identify the symmetry, right? So what is this thing invariant under? Let's say, I mean, apart from like the phase rotation. Exactly. So if we do this, but then we would have here, right? So this thing would flip to -8. So how can we compensate this?
You also flip OX.
Exactly. So the symmetry, the Z2 symmetry in question is Z2, which is K2 minus A, by having by daggers minus X. And as someone correctly, I think, suggested, that, I mean, this symmetry reflects the parity conserving nature of the interaction. Then, namely, so yeah, our Hamiltonian commutes with the operator, which is P is equal to -1 to the power n x. Right, we so this is like a fancy mathematical way of saying that. Yeah, like if you excite the atom, right, you absorb a photon, and vice versa. Right, this is just like a fancy way of saying this. Right, but like the symmetry question is this, right? So when it's not broken, right, it's clear that like if your A is invariant under, so like if it's not spontaneously broken, right, you cannot have this thing. You cannot have this, right? And likewise, by the way, you also don't have expectation value of sigma x. But when it's spontaneously broken, you have expectation value of A hat, and likewise, so the bottom condensate, and you have also non-zero expectation value of sigma x, right?
Should be a combination, right? Because that only you need also the SN symmetry of the spins. Otherwise, you could break the boundary rotation body, but it doesn't keep their square root of n.
Sorry?
You have well, the zeta 2 and also an SN to the permutations of your spins. And that is responsible for that should be responsible for the square root behavior.
I mean, okay, so, well, I mean, this is, I mean, okay, what is essentially, yeah, somehow like responsible for this, like SN, right? It's, again, it's like a fancy way of saying that you have a flat spin, right?
Yeah, but the point is that because I could change. So suppose that.
I see, like if instead of like having a flat spin, right, you would have something that like would break this SN.
No, I mean, well, that I instead of having a lot of smaller spins, I put only one but big, like huge spin. So I have another classical parameter that will be the size of the spin. That will be, for example, that M spin. No, it's not that one. So instead of taking n spin, n1 of the spins, I take only one, but n is not large enough. So I will expect it that in that model happens the same, but the fact that we have my photon condensation as mentioned, I will be that will be whether the degree of freedom of the band, not only the local parity that is going on in your model.
okay, maybe I still like didn't get like didn't I understand it like what you want to have is instead of having n splits, do you want to have like instead of like n spin 1/2, do you want to have spin m half, let's say?
No, because the one will have a
But
linear
what-
space and the other will have an exponential. You have to think more in careful in the relationships with the both spaces. But yeah, the one is
You could keep the information using clash normal coefficient, then you find a state that is eigenspin of all the states together, and also eigenspin of a few other pairs. Then you can keep like this state is inside of one.
yes, yes. Yeah, could be that. The point is the photon condensation and the equation is only something about that symmetry breaking.
I mean,
or is
like,
it-
let's
or is
say-
the fact that I have a huge back.
No, this part is only about Z.
Okay.
So the question is, so if you had only one spin,
I mean, then probably it would not be quite square, and like, you know, like, but
Okay, yeah.
for obvious reasons, so to say, right? So then n is equal to 1. What can you do? All right. I think here we go. We still have some time. Okay. So now let's say we establish that there is a phase transition, right? That at the very least, like this relatively simple model, right? It has some physics behind it, right? So like some potentially interesting physics behind it, and we want to, of course, somehow address it, right? So we want to so maybe ask following questions, right? So we know that as we increase G, right, or let's say we suspect that as we increase G, right, at a certain point, our symmetry is spontaneously broken, right? And we develop a non-zero expectation values and all that. And this is what we can, at the very least, expect from the steady state. Right? So how can we determine this critical value of G, right? That is one question. And maybe even at least like in this course, right? I think it might sound even more relevant. Okay, how do we reach this steady state, right? So we might also want to consider the dynamics, right? So before sort of going to the functional 2PI formalism and all this, right? So let's try to do something simple. So namely, recall that for observables, right, you have, let's say, have like a conjugate Limblad equation, right, but for observables. You can write it for the density matrix, or you can write it for the observables. Plus right. Now, so in our case, we have gammas, kappas, phase, and so on and so forth, right? And after some simple algebra, one finds following equations. Write them down. We have this minus d x. And I sort of like I dropped the indices because of like homogeneity and all this, right? So like you can take whatever like spin, right? So you want to sort. Oh no, actually. This is weird. Okay, I'll need to check some notation confusion. sigma z g square root of n on y. And please check some like square root of n vectors, because in my notes I say with this equal to this. So like some average scheme, but then I never use S, so I'm a bit confused. What did I try to like? What did I mean? So I wonder like if these are divided by n or not. I need to check it. But that's or maybe later. I think I do it. I think that should be correct. Yeah, with okay, I see. I guess I see what I'm doing. This is more like the setup of the. Anyway, the point is that this system of equation is not closed, right? Why? Because here we have equations for the expectation value, so a sigma x, sigma y, and sigma z. But on the right hand side, we have also 2-point correlation functions, right? So, all right. In principle, of course, we can now, instead of a sigma x, sigma y, sigma z here, use, let's say, a sigma z, right? Derive equations for the missing bits here. But I think it's kind of like easy to guess that on the right hand side, we will have 3-point correlation functions there, right? Then let's say, okay, like we'll get there, right? So we plug in the 3-point functions here, we get the 4-point functions on the other side, right? So this leads to like this infinite hierarchy of equations, right? A la BBGKY or something like this, right? Where the equations for, let's say, n-point correlation functions depend on n plus first correlation functions, right? So how do we sort of close the system of equations, right? So one obvious way is to say, well, you know what? So at a certain point, let's say my higher order correlation function, the 2-point correlation function, is a product of 1-point correlation function. So this is the simplest approximation, right? So that it truncate already on the 2-point level. This would lead to the mean field approximation, right? Alternatively, by the way, so going back to, let's say, this Green's function, all this a bit, right? So what you actually do here, right, if you wish, so instead of this, what you're saying is this, and this is what? When you subtract like the 1-point functions from the 2-point function, you get what?
The
Connected correlation function, or also like in some other areas, it is known as the cumulat. So for this reason, this type of expansion or truncation scheme is known as the cumulant expansion, right? So you just say at a certain point that I don't care about, let's say, 4th-order cumulants, and then you end up with a cumulant, a system of up to 3rd-order cumulants and so on, but that closed, right? Okay, so I will give, let's say, the very quickly. Oh, yeah, so yeah, I think I'll finish. I can erase all this, right? Whether any questions in the chat name? Are you telling us that the Lindblad-Master equation also works for other operators, not only the density metrics? Well, I mean, it's similar to like, how Schrödinger equation, like you can either like, let's say, work in, let's say, it doesn't have to be Lindblad, right? You can solve a Schrödinger equation, right, in which in the Schrödinger picture, right, and then sort of like your operators are time independent and all this, right? Equivalently, you can go to Heisenberg picture, right, in which your operators are time dependent and you have equation like Heisenberg equation governing their dynamics and so on and so forth. But like sort of like the state is static, right? So here it's the same. You can either like work with, let's say, time evolving operators, right, or you can work with time evolving state, right? So time evolving density metrics, right? So the Lindblad, I mean, it's not that like it works for both, right? It's just like two, let's say, two sides of the same equation, right? So you can like reformulate in terms of, say, in terms of the observables.
I got a question. I just wanted to know, last one. So, we can see the, only of the prepared.
Oh yeah, I mean, okay, that's a good point. I think yeah, it's omega naught. That's a good. I think this one is yeah, they're very nice. I think let me check. Yeah, this one is like it's the two levels of like the detuning, right? Yeah. Sorry, yeah, because I mean I like let's say in my actual like nodes that I like work with, right? I use a slightly different notation, but then for whatever reason, I thought, oh yeah, I'll adhere to like this notations, right? And it sometimes it leads to, you know, things like this. So the moral is stick to your guns, right? So like do what you do, not others do. Not have confusions.
You may have understood.
But to what we see up until now in the course to derive the equation, we have to trace out the density matrix. But is also, I think it was like, I mean, it was mentioned in the lecture by Jamir. And it was sort of left as an exercise. I mean, let's say it's, yeah, so that like the equivalent equation for the Lindblad, so like for the observables, it was left as an exercise because people asking.
So just believe and do.
Believe and do, and yeah, better do. And, you know, better do than believe. Unless it's me. Which case, that's the usual thing. All right. Yeah, so if you approximate a sigma alpha A as sigma alpha A, right? So you get the Minicourse equations, right? You have dt alpha. Sure, that's like worth it. Okay. You can all like do it yourself. And I think this is, yeah, like this is where like this notation sort of like comes. That should be, I don't know. Check this, please. The ones. X, Y. All right. And this is something that, first of all, you can just plug this in, let's say, Mathematica or anything, right? So, and play with it, right? So the mean field equation that governs the Dicke dynamics in the presence of photon losses, right? And in principle, also like now, if you want to find a steady state solution, right? Steady state, right? So what you have to do is now 0, 0, 0, 0, right? And what you will find is that the steady state, by the way, I mean, I always like, so it is always implied that if I skip something, that do it yourself, right? So it's very exercise. Like the steady state solution is given by. So you would see something already very suggestive. Only because that. Oh, this. And finally, yeah, right here. Are not to be confused with the complex conjugate, like steady state solution. These were done. So now the condition, right, is that, look, here we see something, right? Like, this thing, like when is it like, say like non-zero and so on, right? So this condition, so you just, let's say you plug this in here, right? And then you see at which G you have a non-zero as X, right? And the point at which it happens is the mean field critical value of the coupling G. It is given by the G critical mean field from this 1/2 divided by. So we found the mean field. Yeah, sort of the mean field result for the critical coupling, right? In principle, you can also play with the equations, sort of like you also get dynamics, right? Again, you in principle, like if you play it more, you can see that find the critical exponent on the mean field level and all this typical good stuff, right? Associated with phase transitions, plus the dynamics. However, right, I guess we want to do a bit more, right? And let's say if we wanted to do more, if we want to go beyond mean field using the cumulant expansion, right? The problem is it is, let's say, not self-consistent, right? And as such, it is sort of prone to eventually blow up. In the sense, sort of like it's kind of similar to what Aleksandr this morning was saying, that like these perturbative sort of expansions, not self-consistent expansions, right? They tend to have these problems with circularity. They tend to have problems with conservation laws. All this, you know, not a very nice stuff to describe your dynamics, right? So for that reason, next time, and I think it's about time to finish. Next time, we will put everything on a Schwinge-Keldysh contour, do the 2pi, derive the Dyson equations or the Kadanoff-Böhm equations, and then hopefully I will also even cover a bit how you can do this on your laptop, and we can even maybe play a bit with the numerics. So the goal is that by the end of this course, you should be able to, in principle, repeat all of this and have your own 2pi Dicke model code. Yeah.
Written in? Written in?
In my case, in Julia.
Should we allow?
Yeah, I'm not sure. Okay, I'm not sure. Like, if you, if we actually were gonna play with like the code, right? I mean, probably not. But sort of like, I will show some like, you know, simulations and so on, right? I mean, I don't expect you to sort of.
So you're also a Julia.
Julia language, yeah. Julia Camp, yeah. Of course, of course.
Okay.
Okay, I think this is it for tomorrow, unless you have questions.
Let's be so, it's not a girl.
Sorry?
Julia is not a girl. Let's.
Julia language, Julia language.
Best that C easiest byte.
It calls a lot.
Change. Yeah, but you are like considering the case in the paper already. Yeah, exactly. So like in one case, let's say, like in the case, Right, but it's a unit. Principal facing out. I see, right, yeah, it emits and then like, it brings information about, right? So like, the decay that is like captured is the one that, like, if it's a body that stays in the chemical, right? So information remains in the system that we can process, right? Where the other case, and comes to the